Hello everyone, this is lecture 8. We will try to do some practice so that it would help you for the next lab, which will be on Thursday. First of all, for the assignment that was just completed in the previous lab, there was a question, what is the mantissa for the real value -1? And in the floating point converter, in the online tool, it shows that the mantissa is indeed 0. If you chose to put 1 in here, that's incorrect. It actually gives you the result -1.5. If you don't know why that happens, take a look. It's very important that you understand what's going on. On the quiz for the second lab, there was a question, not exactly like the one that I'm showing, but very similar. Let's look on the left. We're doing with logical variable, also known as Boolean variables. And there's an expression that goes like this. B is not true or true. First of all, let's look what OR does. There is lecture notes number 7. They're available on Brightspace. There's a table over here that shows different logical operators. One of them is OR. Now, true or true is true. Actually, everything is true unless both are false. So think of this. If we execute this statement on the right first, so true or true, the result is true. You negate that, you get false. If you negate first, not true gives you false, then false or true gives you true. So the order of operations matter. To jump quickly to the conclusion of this discussion, not is executed first. It has a higher precedence. If we run this code on the right, this is what it shows. So by default, this is what happens. Not true gives you false, then false or true gives you true. The answer is true. If we specifically put the parentheses on the right side, then this will give you true. Not will negate it, make it false. So it's very confusing. Just keep in mind that it's not a binary operator. It's more of a, like, I think called either singular. Let's look at statement line 4. Not 1 greater than 2. In here, you cannot really apply not to the integer 1. So not waits until the comparison gives a logical expression as a result. So 1 is greater than 2, it becomes false, and this is executed first. Even though some books, they say that not has the highest precedence, in practice, comparison goes first, negation next. If you specifically try to put parentheses, like if you try to write something like b equals, let's look on the left side over here, b equals not 1, this will not compile. This is a syntax error. Finally, just a matter of notation when comparing values. Not equals is written like this. It's the slash equals. It's not equals. It is identical to just having not in front of the equals. There will be a problem on the next lab quiz that will give you something similar to this long statement with not and or. Also, what will happen if we'll have not false and false? what will be the result of that. There is a whole lecture note on if statements and select case statements. We've done this already a million times. So the if, then, and if statement, this is very standard. That's the one you used. It's also possible to write a one-line statement like this. There will be no and if, and there will be no then. So if something, then do what you want to do in just one line. So print something out, assign something. There is also operators like exit to exit the loop or continue. We will move on to them next. And then if, then, else, and if. This is self-explanatory. I'm sure you guys know this. We also had select case statement, which is exactly as if statement, just different notation, just a matter of notation and syntax, and nobody uses select case ever. So let's move on to the next example. So another very quick example. There is this example code that just prints out the results of some functions that exist. It's just for you to know what functions we have in Fortran to use. Let's look at the first one. Inverse tangent of 1 will give you pi over 4. That's just by its definition. So to program pi into a Fortran, an established way to do that is to assign it to inverse tangent of 1 times 4. Now we have, for example, sine of pi over 4. You know what it should give you from mathematics, square root of 2 over 2. You can compare those values on the right. This is the output. Gamma function is the one we talked about. Gives you factorial, but you have to add 1 when you take in the gamma function. So gamma function of n plus 1 is the factorial of n. Max, we haven't used that, but that's self-explanatory. You can put any number of parameters in there. Remainder of the division, a random number. It is random to some extent, but the first time you run it, it's not random. Keep in mind, it'll just keep repeating the same sequence over and over since every time you run the program. If you want truly random numbers, only some processors have that special instruction to generate number from the static noise of some sort, from fluctuations of temperature and so on. Another option that programmers used often is look at the clock in the computer and initialize the random numbers from the given clock. So every time you restart the program, unless it's exactly on the same date and second and millisecond, then you will have a new random sequence. Hyperbolic tangent and just any hyperbolic functions. They're hyperbolic sine and cosine. It's identical to this expression. Natural log. 2.7 is an approximation of Euler's number, so we expect the result to be near 1. And we have log base 10. If we take the log of 100,000 something, it will be near 5. So as expected. So that's that. Another topic that is related is mathematical expressions and algebraic expressions. So in this course, we talk about calculating mathematical expressions, especially the ones that deal with multiplication, division, subtraction, and addition. This is what processor does. We also can have, in mathematics, we can express other things using different notations, such as roots. Squares is basically multiplication. What this article talks about is different categories of mathematical expressions. So the simplest ones you would have, for example, let's look at this table, would be a constant. So constant does nothing. It exists. Everybody's happy. You can run some elementary arithmetic operations on it. So you can have addition, subtraction, and multiplication. You can have divisions, but in polynomials, you don't have divisions. There can be something that we already seen. There can be a sum. We only deal with finite sums in programming because we cannot run a program infinitely. We know that at some point something happens. Either the value that we're trying to compute doesn't change anymore. Another expression, such as a finite product, we've seen this in the factorial. Finite continued fraction. Now that's getting more complicated. You can read about it, what this looks like. It's something like you have an expression that divides by another expression. Let's look here in the illustration on the right. By another expression, and so on. Now, if this fraction is finite, we can compute it using division and addition. Rational exponent. If your exponent is a natural number, like 3 to the power of 3, it's the same as the finite product. If you have a rational exponent, 3 to the power of 3.1, then, well, it's a root of some sort and an exponent. But you can see how it's getting complicated. It's not very clear already how to evaluate that. There's also just nth root. Also not really clear. In Fortran, there's no cubic root function. If, for example, somebody asks you to calculate cubic root in Fortran, you'd have to come up with something because it doesn't really do that. Now, let's skip this to, so we've seen the exponent function in Fortran. We've seen logarithm and trigonometric functions. They're sort of given to us. How they work behind the scenes, it's still a mystery to some extent. You can think of its Taylor series, or it may be Legendre polynomials approximation, which is more likely. But their expression, for example, such as we've seen gamma function. And we talked how gamma function gives you a factorial if it's given an integer. But let's look at how gamma function is defined. And it's an expression of this type. Gamma of z would be an integral from 0 to infinity. You probably haven't dealt with integrals just yet, if you only completed Math 1000. The point is, none of this looks like what we would compute in Fortran. So anything that goes in this red area of this table requires a lot of mathematical trickery to convert it to something that computer can crunch. And basically the computer just crunches arithmetics. So we'll have to bring whatever is in this area we're trying to calculate. The integral, by the way, is all the way at the bottom. That's one of the most difficult things. Their infinite sum, which we can try to approximate with a finite sum, and so on. So I just wanted to show you this table because these concepts, they're more of a mathematical and even some degree of philosophical. It will not be on the test. It's just the knowledge for you to see what fits in the computer, what computer does, and where mathematics stand. Let's continue with a different topic. Notice how the format strings here are shown. We have a character string of 20 symbols. that will be printed out first, and then a floating point value of length 15 with 7 decimal places. Also, let's look at the format descriptors. We already used most of them. We have not used this parameter on the left. If it's present and if it's bigger than 1, it's identical as just repeating this expression r times. So if r is 2, it'll be the same as I, W, I, W. Now, you cannot just put W onto the format string. You have to give a number to it, like 10 digits. It's not going to really give you 10 digits. It's going to be the number that's 10 characters long. If you add this .m, m will force it to print out a minimum number of digits. So I suppose it will print out like trailing zeros in the front. F is the most sort of human readable form, but it's not the most useful when talking about accuracy, because F will print on the left of the decimal point. It will print whatever comes before the decimal point. On the right, it will print the number of the number of digits D. The thing is, we only know that for single precision reals, only 7 significant figures are there. So if you already printed 6 digits to the left of the decimal point, only 1 will be the significant digit, and the rest will be gibberish, as we already saw many times, right? So in this sense, the exponential notation is the most the one that makes the most sense, because you can give it the number of digits as 7, and it will print out all significant figures that are in that number. Of course, it's not always human readable, because it will always print out the exponent, which can be, in case if you're a physicist and you're looking at galaxies, yes, that exponent will make sense. It will give you large numbers. If you look at the scale of atoms, it will be very small, also makes sense. But sometimes you may get numbers like 0.1 times 10 to the power of 2. And for a human, there is just no reason to confuse like that, because we will just write 10, right? So scientific notation is very similar. It will just print one number to the left of the decimal point and the rest on the right. Not on this list. There is B for binary. L for logical data is on the list. There is A for characters. We've already seen that. X will just give you like horizontal spacing. It will put like as many spaces as you indicate. And there's vertical spaces. And you have to put everything usually into parentheses like this. There is another example that goes along these lines. This one deals with strings. Strings is a big topic. We have to start talking about them. Strings will be sort of our transition to using arrays, because strings are actually arrays of characters. And in Fortran, it's special. There is a special treatment of strings to simplify just dealing with them. So they're not really called arrays yet, but internally they're exactly the same thing as arrays. So each symbol in the string, in this case, it's represented by a single byte, and byte can only handle value between 0 and 255. So there is at most 256 different symbols. Of course, we don't even need so many because the alphabet is much smaller. But think about Chinese alphabet. Chinese, I don't know if it's called alphabet, but Chinese list of symbols, they have more symbols than can fit in 256 placeholders. Let's see how Latin symbols, letters are represented in this table. So there is something called the standard character table, and it matches the numerical representation of the letter to the letter. So we can, for example, take a byte, write into this the value 87, and then tell the program, okay, now interpret this byte as a letter, and it will think of it as large W, uppercase W. Not every symbol is printed. Some symbols are made to start a new line, such as this carriage return symbol, I think CR. Some symbols, it's just your space. I think it's this one, 32. There is an escape key. It doesn't really even print out. It's just something that is received from the keyboard if you type it. There are other ways of encoding letters, of course. I explained the problem now that there is now more letters. In the past, computers were weaker, so they only held this limited small table. Now these days, it's no longer a problem to put any symbol in the world into some sort of standardized table. There's a lot of those emojis, and there's like thousands of them. They're also now standard symbols which you can type and represent. It's just they're treated differently. They're no longer single bytes, and then there's different standards on encoding them. So that's a topic for the future if we get back to this. Let's look at the strings. You can try to assign a long string just to a character. What will happen in this case, if you don't put any length specifier, it will be just one character. Let's run this code just for the illustration. For the first example, it trims this whole string into just W. It calculates the length as being 1. Second string, the length is given as an asterisk symbol. Its length will be exactly the number of the symbols. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5, 6, 7. So 27 symbols in this string as expected. The next one, we specify that it's 30 symbols long. We only initialize it less. And when it's printed out, there's a lot of space left over, so the rest is filled with space. If we don't allow enough space, so let's make a string of 10 characters, try to assign it to a longer one, it will just trim it, in this case to 10, and the length will be as specified. There's also a possibility to have a dynamically allocated string of variable size. Whatever you put in this, it will hold. There is advantages and disadvantages to that. The string will now be placed on a heap. The computer will decide how much to allocate the moment the assignment takes place. The disadvantages here is if you have many of those and many allocations as well, you can make fragmented heap, because you will, if you're working with the strings, you might be erasing them from the memory and creating the new ones of the different size. So you'll make the heap portion of memory look like cheese, where some of the fragments are no longer needed, they have been deallocated, but that space cannot really be reused for any larger strings. Even if you put some smaller strings into these larger spaces, there will still be portions that are of the unused space. Why is string similar to an array? There is this operation substring. It is written like this. So first name your variable, put the name of your variable, and then in the parentheses, one number, colon, other number. You take out a range between symbol 5 and symbol 25. So let's look here. This was the original text, and that's the fragment that was taken out. Now, if you just put 5 and 5, actually this will be space, but the point is you will cut out just one single symbol from this whole array, so you can have access to them individually. So you're already dealing with the arrays over here. Also, if you have the substring, not only you can print it out, but you can assign to it. So we can take the substring and equate it to something else, and we'll basically write data in the middle of this string array. A few other things. Usually when you're talking about strings, you want to find some text in it. Now, in this case, we're going to try to find the word runners. And indeed, it can be found at location 215. So here it is. And you can also concatenate strings, written as double slash. So first string, double slash, another string, you concatenate them together. You can see here it's placed in string 4, so it overwrites everything that was in here previously. And now the result of concatenating string 1 and string 2 is two strings together. Also, I've seen students already doing this. Somebody printed a new line. That's great. If you need to insert a new line for some reason, not just between two strings, but maybe you print out some results and then you want a new line, here's an operator that will give you a symbol for the new line. This concludes our discussion of strings for now. We will get back to them, and we will start talking about arrays soon. Arrays, of course, they give much more freedom for the program. Without arrays, right now we're very limited in the algorithms that we can try and look at. Let's look at the last example that is here prepared. It is an algorithm. It's a mathematical algorithm that does not use arrays. It generates a sequence. The reason for this exercise is to talk about loops once again. In the lecture notes 8, it discusses do loops, and there's an operator here that's written as exit, and then there's also one that's continue. So let's talk about that. If you have a do loop and you put an exit in there, the loop will be terminated. That's just as simple as that. Let's find an example, if it exists here somewhere. Here's an example of the do loop with an exit. If the sum is greater than the limit, exit. Of course, the way it's written here, this condition could have been placed into the while condition. It would give the exact same result. But sometimes you need to exit somewhere in the middle. You cannot do this in the beginning. You cannot really do this in the end. Sometimes you need it in the middle somewhere, and exit will exit the loop. Sometimes another possibility, you may want to continue with the next cycle of the loop, and that's the operator continue. So it will forget about anything that's written below. It'll just go back to the beginning. So that would be continue operator, not exit. Continue operator also makes sense in the case of multi-threaded programming, where you have a library such as OpenMP that will allow you to use all the cores of your machine for a loop. In this case, if you try to exit the loop, it will not even allow you to write the statement like this, exit. It will have to complete, like if you give it like a loop from 1 to 1,000,000, it will have to complete all of them. It will split them between the cores. But what you are allowed to use in the loop though is the continue operator. So while your loop runs, if you run to some point that you want to terminate this whole process, you cannot really get out of the loop, but you are allowed to do the continue operator and quickly basically rewind all your loops on the multiple cores to the end of it. So continue is still used. Let's now look at the strange algorithm. The algorithm is called Collatz. There is a long article on Wikipedia. It's called Collatz conjecture. I will not gonna make you go through this. Let's just start with the first few things. So there is a function that operates on integer numbers. And the function goes like this. If you give it a number that is even, that is if it divides by 2, the result will be the same number n over 2. If it's given to you as odd, the result will be 3n plus 1. As simple as that. And we implemented function in the Fortran code on the top over here. The function, we call it next element. It's given n. A few things here. We need to start working with other types of data. So you've already seen integers as in 4-byte integers. We've seen that it has a certain limitation of about 2 billion something. Now we can have 8-byte integers that will hold more numbers. So these are the ones we'll use in this example. Then we'll do the operations that we just discussed. If the remainder of division by 2 is 0, then it's an even number. Then we output n over 2. Otherwise, if the number is odd, we'll do n times 3 plus 1. And the function, we're good. By the way, those 8-byte integers, they can hold this maximal number. The point of this code is to illustrate conditional statements, like if, show another do loop. Unfortunately, as hard as I tried, I couldn't come up with an example where you would use exit and continue. Now, scientists do use them. It's just an algorithm. It would be an algorithm that is fairly sophisticated. We get a user input. We start with something, and I actually suggest that you start with your student number. Just give it your student number as a starting point, and the program will continue. Let's run it. the way that my terminal is set up, I cannot really scroll up. And I'll try to do this. I'll try to do vertical line more. I think this is how it works. All right, so now for me it will print out screen by screen. So let's look at this. We started at the number 1234, 1234. This number is even. It is divided by 2. And then we are into our cycle. So the next one is even. It's divided by 2. Even divided by 2. Then multiplied by 3 plus 1. Divided by 2 again. And it keeps going. So next page. Next page. And at the iteration 141, it collapses to 1. Now there is something interesting about this sequence. So Collatz conjecture, it's not a theorem because nobody has proven it yet. It's difficult to prove. The conjecture is any number that you will put will collapse to 1. A very simple idea. Nobody knows how to prove. And the mathematicians themselves, they suggest that you stay away from that. The sequences that this algorithm generates can be represented in various interesting ways. Of course, when you start with a certain number, it will follow a certain sequence, but then it may merge with another sequence. So if we started, for example, with number 10,592, we would already be at step 112. So not all numbers give you unique sequences, but rather they're more likely to merge into another existing sequence. And there is a variety of different illustrations, how many steps it takes to collapse to 1, or how would you go from some number into a given existing sequence. So you would start, for example, from 9,670, and this is the route that you would take to arrive to 1. If you start at 85, then this is the location where you start, and you keep going until it all collapses to, there's 1 is somewhere in there. I think this should be 1 in the middle. So to conclude this lecture, let's talk about types of errors that you can encounter in the program. We already talked about syntax errors. It's also possible to have logical errors or bugs. So you would see bugs when you're trying to do one thing, but your code does something else. There's also errors at the type of linking. So this is when your code is syntactically correct, but you're referring to some other function that's not present, that the linker cannot see. It can even be something as silly as the sign function. If the linker cannot access the Fortran standard library to attach to your code, then it doesn't know where to find sign, it doesn't know where to find print. Now, do loops, they're not functions. if statements, they're not functions. So both do loops and select, they will compile to the processor instruction jump. So there will be conditional jump in the processor. Also, any algebraic operations that you do, they're not functions. And exponentiation, so double asterisk, is not natively performed by processor, so that would be a function. An exponent or logarithm, those are functions as well. So yes, so we have the errors in the logic. Again, the program will compile, an executable will be created, but it will not do what you expect it to do. If there is a syntax error, then you broke the rules of the programming language somehow, and the compiler doesn't know how to deal with it. The compiler, it's not some sort of machine learning neural engine. No, it's an algorithm that will crunch what you wrote and produce the executable only if it follows the syntax, only if your code follows the syntax. Linker errors. There is also runtime errors. Your code may work correctly. It may do exactly what you intended, but there may be situations where the program cannot proceed. Say you run it on this remote machine at MAN, on the Garfield computer, and you request 32 gigs of memory. It doesn't have that. It will give you a runtime error that it cannot produce that much memory. Sometimes no error is really produced. For example, there is something given here, division by 0. We already saw you can divide by 0. You'll get infinity. It's not really an error. The error will appear, for example, if you try to pass this infinity to something else, right? So, for example, if you will try to allocate an enormous amount of memory, that may throw an error, or it may not. It's more likely that you will try to allocate a chunk of memory. It will come back as not allocated. If you don't catch this moment, you will try to write your data into the space that was never given to you. And then your runtime error will appear, which is in Linux is called a segmentation fault. It's a fault when you're trying to access the portion of memory that was previously not assigned to anything, and that address space just does not exist. So that's a very common source of errors, which are very difficult to understand because your program crashes. This is usually what it does when it crashes. So it just crashes and it's done. Another runtime error will happen if you compile your code for a Xeon. You try to run it on the Celeron, and it will not have a certain instruction. It will crash because it was never made for this processor in the first place. But it may start though and run to some extent. Two problem sets that were already posted. You can already see them, and you should by now have enough knowledge to address those problems. Thank you very much, and this concludes lecture